In this segment, we're going to talk about perfect hashing using two universal family of hash functions. Let's begin with some motivation. Let's say we have m elements and an n bin hash table, and let's say we're performing chain hashing. And let's assume the hash function h is chosen uniformly at random from a two universal family of hash functions. The question is, what is the expected search time? Let's assume that, let's start with the case that X is not in the dictionary. So S is the set of items in the dictionary. And let's assume let's see what happens when X is not in the dictionary. There's a search item. Let's denote the search time by the random variable X. E of X is going to be the summation over 1 to n e of xi, where xi is an indicator random variable that denotes the collision of x, the search item x, with the item I in the dictionary. And just to be clear, the summation must go from I equal to 1 to m. And this summation is at most the summation I equal to 1 to m 1 over n, because we've assumed that we have drawn h uniformly at random from a two universal family of hash functions, and that's at most m over n. And when we limit ourselves to the case where m equals n, then the expected search time is only 1. Now what about the case where the search item X is not in S? Well, we can similarly bound the expectation on X, but now we need to be a bit careful. And because X is in in the dictionary, uh, we cannot we cannot use the indicator random variable for the item X in the dictionary. Because X will collide with itself with probability 1. So we're going to isolate that by a separate 1, and for the remaining cases we're going to use xi. But this doesn't really affect us much, because when we apply the same way of evaluating e of xi's, we get 1 plus m minus 1 over n, which is approximately 2 when m equal to n. And the important conclusion that we can make out of this exercise is that the expected search time is only O of 1 constant when m equal to n. And the idea of perfect hashing is motivated from this context, but we're going to be a little bit more stringent in our expectation. Instead of requiring an expected search time of O of 1, we are interested in a deterministic search time of O of 1. Can we achieve this requirement? And we're going to limit our focus to static dictionaries, in which we're going to store a fixed set of items. There's going to be no updates to these items, and for this fixed set, we want to be able to query whether an item X in the universe is present in the dictionary or not. And the important thing is we're not even going to require complete randomness. We're going to assume that the hash function we have available is chosen uniformly at random from a two universal family of hash functions. Before we proceed, let's recall the balls and bins result that we have. We have m balls and n bins, and these balls are hashed into bins using a hash function that's chosen uniformly at random from a family of hash functions. Then we know that the probability that the most loaded bin is more than m times square root of 2 over n is at most a half. So if we want constant query time, we have to ensure that this m times square root of 2 over n is 1 or lesser. Okay, and this will mean that n has to be at least 2 times m squared. Okay, and when we set n equal to 2m squared, the probability with which we get a collision with which we get a search time of 1 is at most a half. Suppose we pick a hash function h drawn uniformly at random from this family of hash functions, and we hash each item in the dictionary to its location using this hash function. With probability at least a half, we're going to get no collisions at all. Which means that uh, if we tried to construct such a static dictionary, with probability half, we will succeed in getting a perfect hashing, wherein the search time is at most O of 1. And this is a simple um, uh, Bernoulli trial, and if we want to insist on a success, we simply repeat it until we get a success. And so with expected 2 times, we will be able to get a static dictionary in which n items are mapped into 2 m squared locations, and the query time for any item is at most a 1. So all of this discussion motivates what we call perfect hashing. So we want to store a static dictionary, and we want to have that implemented as a hash table. And the key requirement is that our query time in the worst case must be O of 1. And as we have just seen, if we are allowed to use a lot of, a much larger table, so if we are allowed to use a table of length at least 2m squared, then this problem is already solved. That's easy. We just repeatedly attempt constructing the static dictionary using the straightforward hashing technique until we get this requirement. Our question now is a little bit more challenging. How do we construct such a hash table using only a space that is proportional to the number of items? And remember, we still want query time to be constant, not with high probability, but deterministically. Let us remind ourselves from the previous segment that the number of collisions exceeds m squared by n with probability at most a half. And when n equal to m, the number of collisions will exceed m with probability at most a half. So here's an idea for how to construct this perfect hashing. We try hash functions until the number of collisions is at most m. And of course, we can, by the probabilistic method, we can keep repeating our choice of h until we find a hash function h that satisfies this requirement. Okay, and but this is not sufficient for us because now there are collisions, and so some of the collisions, some number of collisions can happen in the same bin, which means that the query time need not be O of 1 anymore. But here's what we do: whenever an item collides into with another item, that means that particular hash location will have multiple items in it. We So let's say that means that we create a chain of length ci at that location I. What we do is we take those ci items and hash them using a different hash function into a hash table of size 2 times ci squared. And we choose the second hash function for these ci items in such a way that there are no collisions in this second hash table. But keep in mind, the second hash table has to be constructed for each location where there is multiple items that are hashed into that location. So here's the picture. So what we have is a hash table. So we use a hash function h such that the number of collisions is kept to within m. We know that that's possible, and it can be done using the probabilistic method. We basically repeat until we find such a hash function. So the total number of collisions is at most m squared. So summation over all I ci squared is at most m. So let's focus on one particular hash location I at which some CI items have been hashed into. So the chain there is CI items. What we do is we take the chain of items and hash it into another hash table of length at 2 CI squared. And we ensure that the second hash table has no collisions whatsoever. And as I just mentioned a little while ago, if you count the total number of collisions, basically summation I equal to 1 to m ci choose 2, that's basically the total number of collisions, and that's at most m. We ensured this. Now let's try to it's notice first of all that the search time is O of 1. Let's say we have an item we want to search. We hash the item and look at its location within the hash table, and if it hashes into a location with just one item in it or no items in it, then we are done. We know that either the item is present or not present. But if we hash into a location that has collisions, so there's a chain at that location, then instead of going down the chain, we simply use in that location, in fact, we don't even need to store the chain. We only need to store the hash function used to hash that we use to hash the items in the chain into another table, right? So that hash, we take that hash function and again hash the same item, and that will give us a location inside this second table, and that could be either empty or contain the item that we are looking for. So the query time, it's clear, is of 1. The question is, what about the space required? Now the complication comes from the fact that in addition to the original hash table, at each location where there were multiple items that were hashed into, we took those items and we created a separate tables for each one of them. And now many such tables could be created. So the question is to ensure that the total space that we have used to create all of those tables is at most O of m. Okay, so let's look at that. So the total space required is at most m plus I equal to 1 to m twice ci squared, because each time there was a collision at those items where there were multiple items that were hashed into, we created separate hash tables of length 2 ci squared. And this, so that's the total space, and that's equal to m plus this 2 ci squared. We want to bring it to a form that we can analyze easily. Recall that n choose 2 can be written as n times n minus 1 by 2, of course, and that's equal to n squared by 2 minus n by 2. So this means that n squared can be written as 2 times n choose 2 plus n, which is what we're going to do here. So this ci squared, we're going to write it as 2 ci choose 2, and remember that's why we have a 4 here, plus 2 times the summation ci. But recall that we know that the summation over all I, Ci choose 2, is at most an M. So this means that we can bound this entire quantity over here by m plus 4m plus 2m, which is at most O of m. So with that, we conclude our segment on perfect hashing. So what we have seen so far is that we can store a static dictionary using hash tables in such a manner that we can search for each item in O of one time. And more importantly, we don't need the simple uniform hashing assumption for this. Instead, all we need is that the hash functions we use are drawn uniformly at random from a family of hash from a two universal family of hash functions.